Today we're going to look at line integrals again, but my goal with this video is to get you to connect something that's happening with what you know to be the gradient vector with line integrals through vector fields. And eventually we'll have to talk about what it means for a vector field to be conservative, but that's probably a few videos from now. So first of all, I want to remind you what the gradient vector is. The gradient vector of a function is the vector whose components are made up of the partial derivatives of that function with respect to each of its different variables. So in this case, there's only two variables in the original function. So we could ask about two different partial derivatives. So we could say what's partial f partial x and what's partial f partial y. You could denote this differently if you wanted. You could say f sub x comma f sub y. You could use the I and j notation if you'd like. All right, so let's compute the gradient vector for this function f. You should know that a function like this, if you think about it, right, it's taking in two inputs, x and y, and it's returning to you, even though this looks complicated, it's returning to you just a single scalar value. Sometimes we call functions like these called scalar functions. You give it a series of variables, in this case just two, but you could have more, but you get back just one number. We call that a scalar function. The gradient of a scalar function, though, is a vector. And so we're going to go through one at a time and take the derivative of all the pieces here. So let's do that. So gradient of f is equal to, if x is the variable, the derivative of 3x would be 3. The derivative of xy squared would be 2xy. And the derivative of the y cubed would be 0. And the derivative of 12 would be 0. And then similarly, if y was the variable, then the derivative of the first term would be 0. The derivative of the second term would just be x squared. And the derivative of that third term there of y cubed would be negative 3y squared. And the derivative of the last term would be 0. So this thing we're looking at here is the gradient vector. Okay, so now what I'm going to ask you to do is just pretend for a moment that we had, and actually let's just correct our notation. Typically with these kinds of vector fields, we usually call them capital F. So if you look at this vector field, we know that this vector field f of x comma y was equal to the gradient of the function f that we had on the previous page. Right? This thing here is the same exact vector function. Okay, so now what we're going to do is we're going to take a look at integrating a function with this, specifically this vector field here, over a curve, or in this case, a line segment. So the line segment we're going to do is going to start here and go to there. All right, so let's remind ourselves, we're going to compute the integral of f of r of t dot r prime of t. You can only do this if you have a function r of t. To get a line between 2 points, we do r of t equals, you always want a starting vector, which in this case, I'll just make that the first point. So it's negative 1, 3 plus, sorry about that, plus some scalar t times a direction vector. And to get your direction vector, what you do is you look at these two vectors and you ask yourself, how do I get from the first one to the second one? So you can see that the x value went from negative 1 to 2, so that's positive 3. And you can see the y value went from 3 to 7, so that's positive 4. So that's our direction vector, and that's going to go here, 3 comma 4. And then our t value, well, if t is 0, then you know you wouldn't be adding anything to the vector negative 1, 3. And if t was 1, you'd be adding the full vector 3, 4 and landing at this location. So that's our domain. All right, so we're ready to start calculating our line integral. We have all the pieces. Quick reminder here, just so you know. Okay, so as I was saying, quick reminder, our vector field here is f of x comma y equals 3 plus 2xy I plus x squared minus 3y squared j. All right, so let's do all the math here. So it's going to be a line integral from 0 to 1. F of r of t means we're going to take this function r of t here. We're going to plug it into our vector field. So let's do a big bracket here. Open parentheses 3 plus 2 times x, which is just, oh, okay, so we better be careful, right? X of t is equal to negative 1 plus 3t. You can see that negative 1 plus 3t. And then y of t is equal to 3 plus 4t. So there we are. So this is going to be 2 times negative 1 plus 3t times 3 plus 4t. And this whole thing gets multiplied, close parenthesis, times I, plus x squared, which would be negative 1 plus 3t quantity squared, minus 3 times 3 plus 4t squared times j. And then this one's times, this whole thing is getting multiplied by j. So let's put a big bracket around it. That'll do it. Okay. And so then that whole thing gets dotted with r prime of t. So r prime of t, the derivative of that thing would be 3i plus 4j. And then you have dt. Now you know it's 3i plus 4j because if you look here, the derivative of that with respect to t is just 3. The derivative of the lower expression underneath it with respect to t is just 4. Okay, so this is an integral in one variable. We just have to be very careful with our dot products and everything should be okay. So what we need to do is take this whole expression here and multiply it by 3. And then this whole expression here and multiply it by 4 and add them together. So in the interest of time, I'm going to pause and then come back with the result. You don't need to watch me bash through all that. You can try that on your own. Okay, so let's see how you did. I ended up getting this, negative 84 t squared minus 282 t minus 113 dt. Okay, so the numbers might not be nice to deal with, but that is a pretty straightforward integral. If we do our antiderivative, you get negative 84 over 3 t cubed minus 282 over 2 t squared minus 113 evaluated from 0 to 1. 113t, forgive me. So it's easy to tell here that if we plug the 0 in, everything would go to 0. So it would be a minus 0 at the end of this integral. So the only thing we really need to do is plug 1 in the beginning. So you get negative 84 thirds minus 282 over 2 minus 113. So let's see what happens when we plug all that in. So everything's said and done here. I'm getting negative 282. So this vector field did a lot of work against us as we move through it. Okay, so what's next? It turns out that's a good place to stop. So the important thing I want you to realize today is to remember, first off, how do you find the gradient of a scalar function? And then secondly, note that we can view that gradient function as a vector field, which is what we did here. And if we have a vector field, then we can compute a line integral through it, which is all this procedure. Okay, so thanks for watching, and we'll see you soon.